nothing ever happened here, as the historic walled town of Conwy returns to a sense of tranquility and normality that has been lost for almost half a century. The town, which has the imposing mountains of Snowdonia as a backdrop, is a living testimony of years of excellence by civil engineers of previous generations, who have created such masterpieces as the castle, the Telford Suspension Bridge, and Stephenson's Box Bridge. But despite their genius, the civil engineers of old were obviously lacking in vision in failing to predict the impending explosion in transport, which over the years has transformed Conwy into one of the most chronic bottlenecks in Britain, causing annoyance and frustration to the local population, to millions of tourists, and also to local industries. Today, though, the problem is solved, and under the swirling tidal waters of the Conwy estuary lies the modern-day solution to the problems once pondered over by Telford and Stephenson, the UK's first immersed tube road tunnel, which took almost 5 years to construct. Now let's look back at what has been a real success for 20th century engineering. It had been obvious to everyone a decade ago that a new method of crossing the estuary had to be found. Because of its beauty, its history, and its general environmental importance, deciding how to go about it became a burning issue. In the end, the more complex solution of a tunnel was decided upon because of its total lack of visual impact on this area of outstanding beauty. The Conwy crossing involves far more than just the tunnel under the river. It includes 6 kilometres of dual carriageway, starting at the Conwy interchange and runs westwards along the shoreline of the Conwy estuary, passing below the river between Deganwy and Bodlondeb Point. The new road then crosses the coastal sandflats immediately to the north of Conwy Mountain. Before work could start on the tunnel, detailed site investigations were carried out, and design schemes were prepared for the temporary works. Work could then begin in earnest on the huge earth bunds that were necessary to protect the sites of the east and west approach structures, and also the 9-hectare casting basin where the immersed tube tunnel sections will be built. Once the bunds were in place, the sites were protected from the estuary's tidal waters. Work then began on the diaphragm wall, which was injected into the core of the bunds to prevent the water seeping through the granular fills into the excavations. This thin wall cutoff, as it is known, was also backed up by a complex system of dewatering well points, vacuum ejector wells, and heavy-duty pumping mains, which remove the groundwater. With the temporary earthworks in place, excavation could progress. In total, almost 1.5 million cubic meters of muck was excavated and removed from these areas. On the east side of the river, 250,000 cubic meters was removed and deposited within the Conwy reclamation area, whilst on the west side of the river, 420,000 cubic meters of material was moved. Suitable granular material, excavated from the approach trench, was placed within the permanent earthworks, and the clays were transported to stockpile areas.
During the first 2 years of the contract, extensive earthwork operations have been carried out on both the east and west approaches to the tunnel. Where the new road has to pass over soft, wet areas of the estuary, large quantities of unsuitable material have been removed and replaced with blankets of rock.
In addition to the tunnel itself, there are 16 other major structures to be completed. Starting at the east end, Bridge 1 is a 230-metre-long 10-span viaduct. The strutments are founded on board-cast 1-inch place piles on the west and BSP piles on the east. The piers are all on steel piles, and the embankment behind the struts is supported on reinforced concrete rafts. The other outstanding structure on the east approach is the N2, which allows the new route to pass below the Chester-Holyhead railway line and the existing causeway flyover.
4 bridges had to be built spanning the walls. Each had to be completed without disrupting traffic on either the main London to Holyhead railway line or the existing A55 trunk road. Without careful planning and considerable engineering skills, the whole of North Wales could easily have ground to an abrupt halt during the summer.
In creating the massive crater to form the casting basin, 750,000 cubic metres of muck was shifted to take the site down to a level of -10 metres, some 40 metres below high tide. And whilst most of the sands and clays could be disposed of on dry land, more than 300,000 cubic metres of the poorer material had to be dumped out at sea using special barges. Contracts of this nature, however, are never simple. Even as works progressed on the excavation of the east cut and cover, site investigations show that the rock formation below shelved at right angles to the line of the tunnel. This required a rethink of the design, and additional piling works had to be constructed below 2 sections of the cut and cover structure. The east cut and cover and the east portal is constructed in 5 separate sections. These are connected by special movement joints which allow for differential movements that may occur during construction. Each section was constructed from its lower end in much the same way as the tunnel elements, and once completed, it was ballasted with mass concrete. The lower seaward end was sealed with a bulkhead, the landward end was backfilled, and finally the lower end was flooded. The west cut and cover was of a similar design to the one on the eastern section, but formed from 2 sections which make it only 120 metres long. The main feature of the western approach is a 210-metre ramp structure, which carries the new road below the existing Morver Drive and on into the tunnel. This complex structure is an articulated U-shaped section, which is linked by steel double omega joints with the whole structure ballasted with 64,000 tons of heavyweight concrete.
It was during construction of this section that engineers hit an unforeseen problem which threatened to set back the whole project. When excavation was almost complete, an unexpected artesian well was found. The solution was ingenious. Boreholes were sunk and pumps were installed. The water was cut off, flooding was prevented, and work could continue.
Where the excavation was completed, work proceeded on this complex structure which provides the access to the tunnel from the west side of the river. The 210-metre-long structure is divided into 9 separate bays, with each bay connected by a semi-articulated joint which is made up from a prefabricated steel double omega section. The base and walls of each bay are made rigid by transverse reinforced concrete ribs across the floor of the structure and counterforts to brace the double wall each side of this carriageway. Once the walls were constructed, the whole of the structure was filled with heavyweight mass concrete to counteract any hydrostatic uplift. This approach structure forms the transition from buried tunnel to open cutting. It's also the point of commencement for another feature of the project. The whole of this structure and its surrounding earthworks are sealed within a continuous plastic membrane. This membrane, which protects some 900 metres of the new road from the inconsistencies of the Conwy Morva's high water table, starts at the Tunnel West portal and runs all the way as one impermeable blanket up to the Conwy Morva interchange. The membrane was placed below the carriageway with all the individual pieces welded together to ensure that it formed a single watertight skin. It was then backfilled with heavyweight aggregates, and finally the road was constructed within this protected environment. The structure for the Conwy Morva interchange is also a U-shaped channel, and like the tunnel's west approach, it's buried below a ballast fill. Motorists driving along the new road will never be aware of the hard work that's being carried out to ensure their easy passage across this once unstable site. Similarly, the bridges to the north and west of this interchange, which carry the traffic into Conwy and on into Gwynedd and Anglesey, have been constructed on extensively piled foundations. In fact, the second of these structures and its approaches, which carries the A55 over the Chester to Holyhead railway line, has been founded on nearly 2,000 driven and bored piles, and the steel deck for the bridge was prefabricated in South Wales and moved into position when traffic was light, often during hours of darkness. Without doubt, the approach roads either side of the river have given civil engineers problems never before faced in the history of major contracts. Future clients and road users will certainly benefit from the lessons learnt by Tarmac and Costain in tackling this project. Never before has there been so much sifting and shifting of sand, earth and clay. But the glamour and fascination lies out here with the bit in the middle. Beneath these waters will lie Britain's first immersed tube tunnel. Instead of burrowing beneath the estuary, the tunnel sections are being constructed on shore, then to be floated out and sunk into position. This is where the giant tunnel sections are taking shape, and the scale of the operation is awe-inspiring. I'm standing some 14 metres below high water level of the river nearby. The space within these watertight walls could quite easily accommodate Wembley Stadium. The external face of the floor and walls of the tunnel is protected by a 6mm steel membrane, which has been coated with high-density urethane. This membrane and all the other steel works for the tunnel sections were fabricated and coated in workshops near the casting basin. The floors, walls and roofs of each unit are constructed in 10 bays. The floor bays each involve 450 cubic metres of concrete. Due to the thickness of the base, particularly at the haunches, care has to be taken to regulate temperature differentials during curing. Concrete temperatures are monitored by thermocouples installed within the concrete, and monitoring data is fed into a microcomputer. tunnel walls are poured in single lifts, using mobile internal steel face shutters, and as the walls progress, the purpose-built roof shutter is installed. The roof again involves a concrete pour of 450 cubic meters, with the added difficulty that the end bays have to incorporate cast-in fabrications upon which the bollards and survey towers will be fixed. As you'll later see, these survey towers will be vital during the float-out of the tunnel sections into the estuary. Whilst the floors and walls are made waterproof by the coated steel plate, the roof is protected by a bituminous membrane. This in turn will be protected by a 150mm layer of reinforced concrete.
It's difficult to imagine, but in little more than 2 years' time, these sections will be carrying the thousands of cars, coaches and lorries that daily pass across North Wales. The statistics are impressive. The 6 tunnel sections are twin reinforced concrete tubes, 118 metres long, 24 metres wide and 10.5 metres high. When completed, ready for floating out, they will each weigh around 30,000 tonnes.
At this stage, the unit is structurally ready for floating out. However, we must look to the ends and inside the units. Steel bulkheads constructed across the ends of the tunnel bores seal off the tubes to make the buoyant caisson. To control this buoyancy, 4 pairs of ballast tanks will be constructed inside each unit. The tanks carry a total of 4 million litres, which can be regulated by a pumping system to vary the buoyancy during the float out into the river. At the leading end of the unit, shear keys are placed to fit into pockets constructed in the adjacent structure. And finally, a facing plate is welded onto the end frames and a synthetic rubber Gina gasket is fixed to the face. This gasket will provide the primary seals to the tunnel as the units are placed in the trench. When all of these tasks were completed, the first phase of the transfer of these enormous concrete units into their places within the estuary could commence. In late August 1989, pumps were switched on and the casting basin flooded. In order that the sections could be transported out of the basin and placed in the riverbed, a large trench had to be excavated between the lower ends of the 2 cut-and-cover tunnels, and a deep channel had to be cut between the basin and the trench. This work was carried out using cutter suction dredgers, which lifted the granular materials from the trench and channel and deposited them in stockpiles adjacent to the East Approach Road for reuse as trench backfill.
No matter how powerful and sophisticated the machinery, there are some jobs where the human element is still important. Up to 70 divers have been employed on the project, working in the main to ensure that conditions in the tunnel trench are exactly right. Some 20 metres below the surface of the River Conwy, they've been operating a device like a giant vacuum cleaner sucking up sand. It's difficult, dark and dangerous. All the divers have been trained to work in the exacting conditions of the North Sea.
The unsuitable materials near the bottom of the trench, which included boulder clays, alluvial clays, and soft glacial deposits, were all pumped to a specially prepared site 2 kilometres upstream at Conwy. This area was allowed to settle and later landscaped to provide a new 80-acre nature reserve. When the main trench was cut in the estuary, the dredger then removed sections of the bunds to provide a trench right across the river, and all that remained before floating out the first section was to place foundation slabs in the trench floor to carry the secondary end of the tunnel elements. But all these works go on deep below the tidal waters of the estuary, and consequently they're difficult to film. The same goes for the works involved in transporting the tunnel units from the flooded basin out to their permanent locations below the riverbed. So perhaps we can illustrate the principles involved through this animation. As we've already pointed out, when the structural elements are completed, each unit is fitted with internal ballast tanks, bulkhead walls at each end, and a Gina gasket at the leading end. The tanks are then filled. Pontoons positioned over the units assist in controlling their relocation and final placing. The whole idea sounds pretty fundamental and is very easy to illustrate, but there's no doubting that the transfer of the first 30,000-ton section from its resting point within the basin and out into the estuary was a nail-biting experience.
Some at steady rate, 40 mil. She's moved about 300 again now. It's coming up 40 mil a minute. It's coming up 40 mil a minute. 176119. 4.5 metres. 14366. You have moved a great deal. Okay. Yes. Keep it here. Can you? They're moving it. Yeah. And the secondary end has gone 1 metre towards element 2.
The pontoons were placed, the ballast tanks were emptied as the spring tide ebbed, and finally, as the tide rose again, on a cold night, the 30th of November 1989 at 9:15, element 1 rose rather unceremoniously off the floor of the basin. It was winched out into the river channel, and as dawn rose, it was plain to all that everything had gone very smoothly. At this point, it was held by cables fixed between anchor points on the element roof and tubular steel piles sunk in the estuary. A special tower was fixed to the secondary tail end of the element, from which all the transportation works would be controlled, and at the forward primary end of the element, a survey tower was erected. Also at the primary end were 2 large hydraulic rams, which were necessary to pull the element home and provide an initial seal, and a support beam, which was used to guide the element home and allow the shear keys to lock onto the preceding element.
193.333. Horizontal 182.019. Okay, thank you. Height 7.058.
Ja, dat klopt. Kleine 3 meter, hè?
On the next neap tide, the element was transported into its permanent location. First it was transported across the river using winches anchored on either side, and once it was at its location point, it was centered up using the lateral control winches on board the pontoons. Although it was originally intended to immerse the elements during the summer of 1989, the additional works on the approach structures made it necessary to reschedule this stage, and work had to progress over the winter period. It was unfortunate that this winter also included the worst storms in living memory.
The complex construction is not the only problem facing engineers. Today the winds are gusting up to 90 miles an hour, the waters are choppy, conditions are far from ideal. Because of the tight schedule, it was not possible to float out the sections during the summer. Come rain or shine though, the job must continue, though some individual operations have had to be postponed for a day or two to wait for better weather.
But the work must go on. As they close in on their final position, the units are lowered to bring the leading face towards the end of the adjacent unit. The locating arm, fixed to the roof, guides the element, and they're drawn home by hydraulic winches. An initial seal is provided by the Gina gasket, and once the water is removed from the bulkheads, it will be compressed by a hydrostatic head of 2,500 tons.
At this stage of construction, we're approaching the end of the immersion process. Only one more section needs to be immersed below the riverbed. This is the secondary end of section 5. Beyond this bulkhead lies the river Conwy and the dredger Orion, which is busy cleaning the trench, ready for the final section of tunnel, which will complete the link between the two banks. Massive as they are, these concrete sections would float to the surface if they weren't held down below the riverbed. Temporary ballast is provided by tanks like this, 4 in each section. During float-out, they were empty. Now the sections are in position, the tanks have been filled with thousands of gallons of water.
The remaining units are all brought into place, and a special closure piece made of 4 preformed sections is completed underwater around the ends of the 6th unit and the west cut and cover. With the tunnel in place, the trench will be backfilled with granular material and the riverbed reinstated to its original form. Before the backfilling works could take place, the space between the bottom of the trench and the underside of the elements had to be filled with bedding material. This was made up at a plant on shore from a mixture of specially graded sand and a cement clinker, and it was pumped via a submerged pipeline to the purpose-built sand jetting gantry, which travelled along the top of the tunnel. The material was then pumped through pipes running down either side of the tunnel and ejected below the element. The gantry started placing the sand bedding at the eastern end of the trench and progressed across the river to the west side. Once sufficient sand was in place, the secondary end support jacks were pulled up and each element in turn was founded upon its permanent bed. The backfill alongside the elements was retrieved by the dredger Orion from the stockpiles and from sandbanks in the estuary and then placed via a special diffuser pontoon. The tunnel was then covered with a blanket of scour protection to prevent the roof being damaged by marine equipment. the elements firmly set in their locations below the riverbed, all the contracted temporary works materials had to be removed and replaced with the permanent finishings. The bulkheads were removed to provide access through the tunnel. Ballast tanks had to be replaced by mass concrete in the tunnel floor, along with service ducts and pipeworks for drainage and fire mains. When the ballast works were substantially completed, work could commence on completing the shear key bearings and placing the internal omega gasket on each joint.
The heavy construction work is now over, but there's still plenty to do. The roadway must be completed through the tunnel. Lighting and ventilation must be fitted. Emergency telephones and firefighting equipment must also be installed.
So on the 25th of October 1991, the dream became a reality. The project was honoured to have Her Majesty the Queen carry out the opening ceremony. It was a day of ceremony and celebration, of spectacular air displays by the Red Arrows flying high above the estuary to signify the milestone in civil engineering history.
It was the first castle, built towards the end of the 13th century, provides an even earlier example of the excellence to which man is capable of aspiring. And it is that very castle, together with its setting in the beautiful and irreplaceable environment of the Conwy estuary, that are the reasons why we are gathered here today to celebrate the opening of a tunnel rather than a bridge. Now that the crossing is complete, and even before the extensive planting and landscaping are finished, the wisdom of going under rather than over the estuary is there for all to see. Our efforts to preserve the magnificent setting of Conwy Castle and the great natural beauty of the estuary will, I'm sure, be fully appreciated by those who come after us.
It was a day of joy for the engineers and workers who turned theory to reality to rid the area of the traffic plague of the modern age. Civic dignitaries watched the event, which heralds a new improved age of tourism, of peace and tranquility, now that the town is rid of the continuous throng of traffic. And so what once seemed just a dream had come true, bringing relief and a sense of pride to the people of the area. They were given a sneak preview in the form of a charity walk organized by local Rotary clubs. So keen was the interest that the event attracted more than 25,000 people, all there to check out their tunnel under the estuary.
The sands of the estuary will now settle down as if nothing has ever happened. The people of Conwy will find a quality of life that has been missing for years. Remember those traffic jams? What traffic jams?